So welcome back to Grade 8 Science. We're now looking at Lab 1, which is on simple machines. Our first example is on the inclined plane, which looks like this. And so the purpose of this experiment is to discover the efficiency of the inclined plane. And what we're going to be doing is we'll be putting an inclined plane, it's a terrible inclined plane, and we'll be lifting up a cylinder and also dragging up the cylinder, and we're going to compare the forces from both of them. So the force to lift it and then the force to drag it. So the force to lift it, we call this force out because this is force without using the machine, and it also travels a certain distance, which we call distance out, which is the distance to make it raise without the machine. With the machine, I have to put in a different amount of force, and I'll call that F in because I need to put in this amount with the machine, and it travels a certain distance, and that's D in, which is the input distance or the distance of the ramp. So if we set this up and we just use a pretend mass, so let's just say this mass is 750 grams. And 750 grams, if I just pull out the calculator. So if we use a calculator, well, first of all, with physics, we need to convert everything to kilograms. So 750 grams is 0.75 kilograms. So given this mass, we can do two things. We can calculate the force, and the calculation of the force is equal to F equals mg. And so force, well, if we'll do the calculations down here, F equals mg, and I know the mass is 0.75 kilograms times 9.8 meters per second squared. So 0.75 times 9.8. Then that gives me the output force as 7.35 newtons. Now we can also use the experimental, which means I'm going to be using something called the spring scale. And so let's say on the side I use a spring scale and I get a measurement of 8 newtons instead. So that's my experimental. So now I have a force that's experimental, an F out that's experimental, and I also have an F out that I'm calculating from the true mass of the actual object. Well, I can also with that information, I can calculate the percent error, which means how far off is my experimental from my true. So let's just create a little line there. So percent error equals the absolute value of the true value minus the experimental value divided by the true value. Absolute value means it doesn't matter which one goes first as long as the answer is positive. While true value in this case is 7.35 newtons minus 8 newtons, all divided by the true value, which is 7.35 newtons. I want to find the absolute value, which means find the positive number, and that'll multiply by 100, and that will give me my percent. So 7.35 minus 8 divided by 7.35 gives me, and then this times 100, gives me about 8.84%. As you see, there was a negative sign in there, but because it's the absolute value, that just means find the positive number, which means just find how far off am I. So I am off by about 8.84%. Great. Now we actually can calculate it using the cart. So now let's say my experimental force was 8 newtons, because that's what I used the spring scale for. Okay, so that was the output. Let's say the distance that it's raised. So for example, if this is my ramp, and the output distance for it to go up was 25 centimeters, which in metric or in in physics, we always want everything in meters. So 0.25 meters. The input, the length of the ramp, let's say the length of the ramp was 100 centimeters, which is 1 meter. Now, if I drag up the cylinder and I use the spring scale, let's say that it required 2.5 newtons. So now with that, I can calculate what we call the mechanical advantage. The ideal mechanical advantage is the ratio of the input distance divided by the output distance. So that means IMA is equal to input distance, so that 1 meter, divided by the output distance, 0.25 meters. That means my IMA is 4. What this means is that it's 4 times easier to do the work, to do the same amount of work, which means because it's 4 times longer, that means it should be 4 times less force that it'll be using to do the same amount of work. The actual mechanical advantage is the ratio between output force and input force. So in this case, my output force is 8 newtons. My input force, what I needed to put in with the spring scale, was 2.5 newtons. So I do 8 divided by 2.5, and I get 3.2. That means, in fact, instead of in a perfect world, it would be 4 times easier. It was really only 3.2 times easier. Why is that? Well, what that means is, first of all, instead of me using 8 newtons, it only took me 2.5 newtons for me to pull up this weight. So, and then, in fact, the work was easier because I didn't have to put as much force. In a perfect world, though, it would have been 4 times. Well, what's the difference between those two? Why is it that the mechanical advantage of the forces is not the same as that of the ideal? Well, it's because we're losing some work to another entity. And as we learned before, work can be transferred, or energy can be transferred to either productive work, which is the movement of it up, and friction. So this is why that it's not exactly the same, because some of the newtons, I need to put in a little bit more extra newtons or force in order to pull it up the ramp. That means that the mechanical advantage is not exactly the ideal that I would want. With that, I can calculate the percent efficiency, which is AMA divided by IMA times 100, or work out times divided by work in. It's the same equation for both. So in this case, the percent efficiency, and I'll just use the second one, AMA divided by IMA, is 3.2 divided by 4 times 100%. 100% efficiency means no friction. That means all of my energy is going directly to productive work. But because in this case, it's not exactly the same. It's 0.8 times 100, is 80%. So this is what this means. 80% of the energy I put in went to actual work. That means I've lost, or I transferred 20% was lost to friction. It's not really lost, it's just transferred to friction instead. But it means that 100% of my energy that I put in did not go to energy using to actually move it up. 80% of it was, but 20% of it was lost due to friction. I could do the exact same thing with the usage of the cart and see whether or not it's more or less efficient to use the cart, whether or not more of the energy I put in will go to pull up the actual weight, or will it be less efficient? And with that, I can make a conclusion. So review a bunch of these concepts of input force, input distance, output distance, IMA, ideal mechanical advantage, AMA, the actual mechanical advantage, and the percent efficiency. If you have any questions, please don't be afraid to ask. So hopefully you understood this lesson.